Please give a warm welcome to Gabriele Bozzola for how to lower the entry barrier to your scientific software.
Yeah. Well, thanks everyone for being here. Last talk of the day. I hope you will stay here once you realize that you've been tricked into attending a talk about documentation. So today I'm going to tell you about how to lower the entry barrier of your scientific software, but I'm much more ambitious than that. I want to almost rediscuss what is scientific software, the role of scientific software in modern science. So first, let me tell you, disclaimer, I'm employed by Caltech. What I'm going to tell you today is my personal view. I do hope my employer shares the same views, but once again, I'm not speaking on behalf of my employer. And I want to, first of all, tell you why I spend a lot of time thinking about scientific software. And so I'm a scientific software engineer. So this means that I'm in this rare position where I'm paid to develop scientific software. And I think this is not super common. Most scientific software, especially in universities, is built by people that don't have strong training in software engineering. Right now, I'm working at CLIMA, the Climate Modeling Alliance. We are developing a next generation climate model for the 21st century. So an open source climate model, a model in Julia, model that runs on GPUs, scales, and something that we need for the upcoming climate change. Before that, I spent quite a few years thinking about black holes. Maybe you remember a picture like that. I spent 5 years in the field of numerical relativity, so we're studying black holes, and numerical relativity is a strongly computational field nowadays, so I was developing scientific software for this type of simulations. And also, on the side, what I do is I review for the Journal of Open Source Software. If you've never heard of this, JOSS, the Journal of Open Source Software, is an open publication, completely run on GitHub, where people, scientists, can submit their code, and other people like me review the code, provide suggestions on how to improve the code, how to make it more maintainable, more usable, and how to ensure that that piece of code is not just left out there in the universe for someone to maybe grab and use, but it's something that we can use as a foundation for new science. So with this, I'm exposed to a lot of scientific software, and I get to interact with the scientific community and people that are building software for science. I'm not going to talk about any of these, but please feel free to ask me any question, reach out to me, stop me after this talk. It's not going to be super long. I'm very, very excited to talk about CLIMA, JOSS, black holes. Instead, I'm going to talk about the following. So for today, what I want to tell you is, first, I want to argue that scientific software has fundamentally unique characteristics and needs. And from those fundamentally unique characteristics and needs arise unique risks, but also opportunities. And I think we can start addressing some of those risks and capitalize on some of those opportunities if we take a user, developer, scientist-centered approach to documentation. And if we do so, then we can move code from just being a tool that we use for science to a piece of self-contained scientific contribution. And I think all of that accelerates science. So this is my thesis. This is what I'm going to tell you today. So you can stop listening if you buy this. Or if you want to be convinced, well, please stay tuned in. So first of all, let's start thinking about why scientific software has unique characteristics and needs. And I could go and list a billion different reasons why I think that's the case. One I already mentioned. I'm paid to develop scientific software. Most people are not. Most people are using software for other reasons. But instead of going through all this bunch of words that I threw on the screen, I'm going to do one of my many experiments that I'm going to carry on today. I'm going to provide a point of view. You are the scientific software here. You are the scientific software. This means that you probably have been developed by a graduate student over the past 5 years. Or maybe if you're not developed by a graduate student over the past 5 years, you were developed by their advisor 25 years ago, and you're still being used, copy and paste, and tweaked over the past 20 years. And people most likely are going to learn how to use you through oral tradition. So there's an older grad student that tells the younger grad student, this is how you use this code. There's not much documentation, and there's a lot of hidden knowledge. There's a lot of information that is required that is around the software that no one has ever took the time to write down. So if I want to use you, well, someone has to tell me how to use you. So there's a lot of oral tradition. And then there's no really automated test. Maybe there's a task folder, but you have to run it yourself. Yeah, we are going to assume that there is a version control, but that's already a good assumption. And then, reproducibility, which we carry a lot in science, maybe it's not that good either, as in maybe there's a specific versions of Python that you have to have, or compiler flags, or you run only on specific machines that were set up with specific libraries. And here, again, we're talking about science. We care about the correctness of our results, because otherwise we're not doing science. We're doing random number generation. So correctness is very, very important. Once again, our goal is moving scientific, science forward. So, this is not a very nice picture to have. These are not very nice qualities. But in all of this, you were used to drive new science. You were used to publish papers. You were used, indeed, to discover new things. And you contain a lot of lessons learned. Those 25 years, those are 25 years of lessons learned. 25 years of, I have to use this specific indexing system, or I have to use this, if I do this, then the code is 25% faster, and so on. This is a lot of very, very valuable information that is in scientific software, that is buried, and that is not accessible, and that we should try to bring up. And in this, you are very, you can be used for future projects. Lots of science is done by starting from something that already existed, changing X, Y, Z, and deriving new results. Science is incremental in many ways. Newton said, I saw farther because I stood on the shoulders of giants. That's precisely what science is. So you can be used for future projects. You can derive and develop science further. So you have lots of potential. Scientific software is exciting. So I think that there's a problem. In our current, the way we think about science right now, I think there's a lot of unrealized scientific potential. There's a lot of unrealized scientific potential because people spend so much time trying to understand other people's code. People spend so much time redeveloping the same things over and over. Or people spend so much time because they're using other people's code and the assumptions are not the same, the code is incorrect, they don't know how to use it. This is a lot of wasted effort. This is a lot of wasted money. This is a lot of wasted time. This is a lot of wasted potential. We are in the era of open source. We are in the era of collaboration. We are in the era in which we can move beyond this, and I can accelerate science. So on one side, I have science killers. I have what I identify as problem. On the other side, I think I have an opportunity. Here, it's not a problem. This is an opportunity. I think if we start thinking about code, instead of being just a tool, instead being in itself a valuable scientific contribution, then this enables more science. If we have open code, code that is easy to extend and use, code that comes with all the knowledge that surrounds the code that is required to extend it and use it. This accelerates science. Code that shares all those lessons learned, lessons that are not published in scientific papers, lessons that are maybe, this compiler flag, maybe this versions of Python. This is what we have to do. All of this accelerates science. So, when we have a problem, there's also an opportunity to do better. So I think if we start thinking about scientific code as a scientific contribution in itself, instead of being just a tool for science, then we can, as a byproduct, we can automatically accelerate science. So I think all of this, in my opinion, boils down to start thinking about documentation in a much more systematic way. I think that documentation is the one place where we can mitigate these risks and move the code from being a tool that is used for science to being itself a scientific contribution. So once again, my end goal here is to remove inefficiency and accelerate science. So now we can maybe have my actual title for this presentation. Today I'm going to tell you about one specific framework for effective technical documentation. So this framework is based on a framework developed by Daniele Procida. Maybe you've seen it. It's called Diataxis. And I extended and I thought about this framework within the context of scientific code. So now I don't remember what Diataxis stands for, something in Greek. But what I care about is that in the framework I'm going to present today, there's two core principles. once again, here we're talking about documentation. Your goal is to be accelerating science, is to be ensuring the code is not just a tool, but it's a scientific contribution. And I think the two core principles that we really should keep in mind are, one, we should explicitly address the needs of users, developers, maintainers, and scientists. So this is one of my core principles. The second core principle is that we should explicitly address how people learn and how people seek information. So with this, I'm going to, once again, allow me to carry you in my train of thought. So I'm going to introduce you to more thought experiments. In the first one, I'm going to introduce some people. I have Dr. Brown. Dr. Brown has a lab that is studying time travel. And the lab has been studying time travel for quite a while and has developed a code called DeLorean.jl. It's a Julia code. It's an open source code that is used to compute flux capacitance. As we all know, it's one of the critical physical ingredients for time travel. So Dr. Brown is a research group. And in this research group, we have Marty McDrive, who's a graduate student. And Marty is interested in learning about time travel. Marty is going to use DeLorean mostly as a user. Marty has to drive to get their PhD. They have to drive science forward. They're going to use DeLorean in new settings that they were not previously considered. And again, for scientific experiments. Then in the same lab, we have Tara Connor, who's a postdoc. Tara has already some experience with time travel. They are already experienced with DeLorean as well, so they will be developing and extending this code to new heights, trying to really push what we can do with DeLorean. And in all of this, Tara also has their own scientific agenda, so they're going to use this code for science. And I hope you can see, if you have ever been exposed to an academic environment, that these are very common people that you find in labs or research groups. And finally, we have a member of the scientific community, Dr. Brownsworth. Dr. Brownsworth, I'm defining them as a competing researcher, so someone that is in the space of in research for time travel, and they're interested in, in studying time travel. And they're interested in DeLorean, not necessarily for anything that it does, not necessarily for the details, but maybe in a very high level, learning what the code can do, learning if this is a good code to use for the Dr. Brownsworth on research, and also learning what DeLorean has developed, the method, the tools, to see if something can be included in the research. So these are three possible users, developers, maintainers, or people interested in this code. And I think these three people identify three verbs that I strongly associate with scientific software. The three verbs I would associate are use, extend, and learn from. I think when it comes to scientific software, use, extend, and learn from the three main actions that I will want my code and my documentation to, to think of. So let's keep this in mind. Our characters are going to come back later. In a second experiment, here what I want to do is I want to identify possible users, possible developers, people interested in this code, in scientific software. In my second experiment, I'll ask you to pick whatever craft you want to learn. It can be cooking, climbing, whatever. And if you think about it, if you were to approach learning something new, maybe you'll notice that there's multiple axes, multiple ways where you approach learning. As in, for instance, we can split learning into theoretical. For instance, you want to learn about climbing, or you want to learn how to climb. So, you learn the theory behind knots and ropes for climbing. But of course, if we have something that's theoretical, we also have the practical side. If you want to learn how to climb, you'll probably have to learn how to tie a knot. So we have started partitioning our plane, your information plane or whatever learning plane, into practical on the top and theoretical at the bottom. There's also a second section that we can perform here. We can look at information while we're learning. For instance, this is a C major. But there's also information that we care about while we're doing. For instance, this is a score. I don't know, a recipe, something that you you care about while you're doing, as opposed to the fear of how to chop a cucumber, whatever, is something that you learn about while you're learning. So if we put all of this together, so we have two axes, we have theoretical and practical, and we have on one side, the second axis is while learning, while doing. If we put all of this together, then we find out that documentation is not one thing, it's at least four things, is while doing, while learning, practical, theoretical, and so on. And it's all from one person. Documentation is for Martin McDrive, it's for developers, it's for users, it's for maintainers, for scientists. So we go back to my core principles. Core principles being, we have to think about people, we have to think about how people learn and how people seek information. So if you, again, partition your plane in 4 sections, you have on top practical steps, at the bottom you have theoretical knowledge, on the left you have while learning, on the right you have while working, and now we can explicitly address these 4 sections. And this is what we do with tutorials, how-to guides, explanations, and references. So these are going to be different sections or different parts of our documentation that explicitly address those needs. And those needs are also needs for people. So we have tutorials that are mostly for using, mostly for people like our graduate students here. There are how-to guides that, once again, are mostly for catered towards people that use this code. Then we have explanations that I'm going to discuss, everything I'm going to discuss in a second, that are mostly for developers. And then we have references that combine everything, to use, to extend, and to learn from. And this is the key of this particular framework for documentation, is once again, if I go back to my core principles, is explicitly thinking about the people that are going to use this code and how those people are going to access the information. So what I'm going to do next is I'm going to go through these 4 sections, +1, and see what each section should accomplish. What is the goal of each section? And what we can do to ensure that those sections accomplish those goals. So the first one is tutorials. So the goals for tutorials is to get the user started, to provide some sense of, I know what I'm doing. Doesn't it feel good when we are approaching something new and we just get it, it just works? And this is what good tutorials are supposed to accomplish. Tutorials are supposed to hold our users by the hand so that we can really help them and ensure that they're not lost. In many cases, for many people, tutorials is the only thing that they're going to say. Oh, I don't get it, I don't bother. So this is really where we have to make sure that we carry our users, in the most possible and most supportive way. Yeah, tutorials have to be correct. That's a great point. I don't have it here, maybe I'll do. I don't remember, but tutorials have to be correct because otherwise, yeah. Yeah, yeah. Well, right. Is it? All right. Anyway, but yeah. So qualities of good tutorials are, well, they have to tell the user what we're going to do. So in this case, we're going to draw that cartoon snake, and once again, our goal here is to make sure that the user stays with us all the time. So we want to ensure that the user sees the result and also see the expected result, so that they know that they're doing the right thing, we're not losing them. And I think this tutorial is a great tutorial, because maybe the eyes are not perfect, but I didn't draw it, so I'm not taking the blame. But this shows the end result. This shows a step. It's single incremental steps that we can follow. And it doesn't provide an explanation about the fear of drawing. It just does. So in all of this, once again, we're just developing maybe the idea of, okay, this is how I'll do a pen. This is, I don't know, very, very simple steps that allow users to feel good, to feel, okay, now I get a sense of what I'm doing. I can move to the next thing. So tutorials are learning-oriented. And tutorials, there's great examples of bad tutorials. Maybe you've seen this. This how to draw an owl. You start with the circle, and then you draw the rest of your friendly owl. Well, this is not a great tutorial. But for users like our graduate students here, this is a really good place where to start, because users can get started, can do something, and once again, can feel good about it. I don't know. Personally, when I'm trying something new and it doesn't work, I don't like that. I want things to work. And good tutorials allow me to be engaged with what I'm doing. And for a graduate student, for a beginner graduate student, this is great. They can start and they can accomplish something without having to keep asking people, and they can start developing a sense of ownership of what they're doing. So tutorials were in our top left corner. Next, we move to the how-to guides, which sound similar, but they're not, because now they're on the right side. So the tutorials were while learning. Now we're thinking about while doing. So how-to guides, they provide steps to accomplish something. How-to guides are like recipes. Even if I've tied my tie a billion times, I still don't know how to tie a tie. So every time I have to look at this picture to figure out how to tie my tie. Actually, a YouTube video, but anyway. Even people that are very experienced with the craft or whatever will probably look up how to deploy a server like X, how to prepare a canvas for oil painting. So this is like a recipe. This is a collection of steps, maybe like a checklist. It doesn't matter. And something that even experienced people will look while doing to accomplish a goal. So here, the difference is tutorial were for learning. Here is for accomplishing something. So what we have is good how-to guides are describe a series of actions to solve a concrete problem. And since they're aimed towards solving something, they kind of have to be a little flexible. There's maybe multiple starting point with the same endpoint, or multiple options. But also, in all of this, they don't have to contain too much fluff. They don't have to explain the entire theory of ties when I just want to tie my tie. So we should omit what is not necessary, and we should just focus on empowering people to get stuff done. So once again, users will love them, because users want to use the code, want to get something done, and something like a how-to guide is a great way for users to do something new, and put maybe multiple how-to guides together to accomplish something that was not covered in the tutorials or whatever. And in between tutorials and how-to guides, there is something that is extremely powerful in scientific software. This is examples. Examples are maybe like this Arduino kit. They can be used in multiple ways. To me, examples demonstrate real-life usage. So this is how we accomplish something. Maybe tutorials are very much idealized. How-to guides are very much self-contained. This is almost like a showcase and provide something that this is how we do this. And we build this kit, whatever, I don't know. But this is like a full real-life example that can be used in two ways. It can be used as a starting point for a new mechatronic implementation of whatever, or can be used to learn how to do X, Y, Z. So that's why I define them as a bridge between tutorials and how-to guides. And I think in scientific software, this is really critical, because most scientific software is copy and paste. We start from something, we change 3 parameters, and then we continue from there. So with this, we ensure that what we're doing is correct, makes sense, and we provide people a way to start with something that makes sense, that is real life, that is scientifically relevant. So now we're thinking about our top section of our plot. So we have tutorial, how-to guides, and we have this bridge with examples. And now we'll move towards the bottom. So the top was practical, the bottom is theoretical. On the bottom left, we have theoretical while learning. So in that case, we have explanations. So explanations provide holistic understanding and clarify the whys. So what I mean with this is, why is this piece of code the way it is? Why is red used in a particular way in Renaissance? Because of pigmentation and chemistry and whatever. So explanations provide broader context, explain why things are the way they are. And once again, in scientific software, this is critical, because maybe we're just afraid of touching the piece of code. We don't know what it does, we don't know why it's there, and maybe the reason why it was there because it was the easiest implementation, or because it was relevant 25 years ago. So explanation make connections, provide context. Once again, I think the way I think about this is clarifying why things are the way they are, discussing alternatives, discussing possible improvements that were not implemented. And in this, we're not teaching necessarily, we're just providing information about our code. So once again, explanations are understanding-oriented. So we're in, developing theoretical knowledge and while learning. This is not something we're going to access while using the code. And this is great for developers, because developers that are handed down some code will feel good and will confident they can make large and important contributions, because then they know why things are the way they are. They can get a mental model of the piece of code, and they can extend it, and they can really understand it, essentially, to extend it. And finally, our fourth piece is references. So references, here I have an example of a so-called visual library. So apparently people in the past, they wanted to know how to draw ears, will look up in books and find, oh, there's 9 different ways I can draw. So references provide the final word on something. This is how this is supposed to be. There's nothing but description. There's nothing about maybe like a dry description. This is the way it is. It's the final word. Of course, references have to be consistent, have to be accurate. And at the end of the day, we're mostly going to use references as we're consulting our references. So maybe you're familiar with, dictionary. We'll go, look up, we'll learn. That's it. And while I'm saying this, maybe you have a picture in mind of what references, function signature, public APIs, architecture, hierarchy. Yes, this is definitely a reference. This is definitely important. But for scientific software, there's so much more. For scientific software, there is okay, what assumptions are we using? What methods are we using? What is the formulation, the formalism? What equations we're solving? What's the meaning of the acronyms that I'm using everywhere? This is where I'm going to define them, so everyone can find them. This is where I'm going to share the hidden knowledge. This is where I provide all the information that doesn't come with the paper, with the code. And in this, I'm going to link papers that maybe influence my work, or papers that I wrote about my code, or my work, where my code was used, and so on. And this, I think, is extremely useful to have a collection of this is what this code is supposed to be doing. And I'll touch upon that in a second. And now you can see if we have this, well, the code is not just a tool anymore. It's essentially an entire, almost publication, is an entire piece of scientific contribution. And this is something that scientists will find extremely exciting, because as a scientist, I don't have to dive deep in your code to learn what it can do. I can just read your page to learn about your method and to see what I can learn from your code. I can see if I can use your code, if I'm interested. I can see if there's good ideas that are worth implementing, as opposed to me going through 20,000 lines of code just to find what equations you're solving. And I find that most scientific code doesn't have this, which is a little sad. But I think this is where we can get most of our improvement, by being more mindful of our code and our formulations. So when you put all together, we have this, maybe documentation metrics. That once again goes back to the core principle. So thinking about how people learn and how people access information and what people were thinking of. So we have our goals, tutorials, how to guides, and explanation, to become familiar, to accomplish something, to build something, to describe. And we have the people that we're targeting, users, developers, the scientific community. We are explicitly targeting an audience, specific audience, and we're explicitly targeting different ways where we want to access information and different moments in time where we want to access information while using a code. So I argue that when you put all together, what you're doing here is you're already lowering the entry barrier to your scientific software. And the reason for this is you automatically provide ramps for people to get in your code. You lower the entry barrier for scientists, for developers, for users, because there is a natural point where, in a natural place where those people will start accessing your code. And maybe, of course, the different groups of people are going to move with time. Users might become developers might become scientists. Scientists are users at some point. But as long as we have clear and explicit entry points, then we can make sure that we're, again, I think, lowering the entry barrier for our scientific software. And in all of this, I also think that we're effectively transforming our code from just a tool, like an instrument, to something that by itself is worth of like a scientific contribution. But in all of this, I have to stress that this is not the final word. This is one possible framework. This is one idea. This is something, like a suggestion if you want to implement in your documentation. But by no means that's the best one. And maybe if you think about it a little bit, I don't know, if you think about climbing, what would it be examples for climbing? I don't even know. This framework doesn't necessarily fit everything. So what I will want to stress here is thinking about documentation and thinking about documentation with in a I wouldn't say a formal way, but sitting down and thinking about documentation is an important step in lowering the entry barrier to our scientific software and accelerating science. So I'm moving towards the end of my talk, and I'm going to give some frequently asked questions. So okay, I only have 15 minutes to work on documentation. What should I do? Okay, if you only have 15 minutes to work on documentation, I strongly recommend you write 2 lines to tell what your code is supposed to be doing. What input it expects, what output it produces. Now, this seems, oh yeah, of course, my description, that's what it does. You'll be surprised to see how many codes are not doing this, or not doing this effectively. Like if you, for maybe their one-line description is hyper-specialized. Only 2 people in the world will understand it, or it's inaccessible. But providing a one-line description of what your code does, it's really valuable. And if you have a little bit more time, what I would recommend, something extremely useful, maybe like an hour, is having one single page that draws the line. This is what my code is supposed to be doing. As in, these are the features that are supposed to be working and supposed to be implemented. And this is useful for everyone because most scientific code is accreted with time. There's maybe experiments that are still in the code base that maybe are not working, or there is a lot of fluff that is not important. What is your code supposed to be doing? Other people can just read that page and learn what your code is supposed to be doing and can use your code, as opposed to digging through the code, understanding what it works, what doesn't work, and maybe 6 months later find out, oh, actually, the feature was not completely implemented, or it works only in specific configuration. This can save a lot of time to other people. So I really, really, really recommend you write a page to say, oh, this is what my code is supposed to do. And finally, if you have much more time, or if you want to be a good citizen of the scientific world, and you want to write the best documentation ever, I don't know what you should be doing. I have no idea. I think that you should just think about, I don't know, my core principles. As in, I think that those are good ideas of like thinking about your people, your users, your developers, your maintainers, your scientists, and whomever might be interested in your code, and thinking about how they would access or when they will use your code. And then structure documentation explicitly addressing those needs. I think this is a good idea. But of course, I'm not claiming to know the final word, so just think about it. Finally, I want to give you a couple of tests that you can try at home by yourself on your scientific code to assess the quality of your code. The first one that I'm calling the survivability test. So you can ask yourself, okay, would someone with reasonable experience be able to independently use and extend my code? That is, if you publish your code and documentation on GitHub, and some different scientist in the same field that has been a scientist for 20 years, so good experience, wants to use that code, can they do that? Or would they require me to walk through all the the steps and provide all the hidden knowledge? So at the end of the day, this survivability in some ways is like thinking about the boss factor, thinking about if I decided not to maintain this code, can someone work on this code or not? Can this code be used for science, or it dies with me? And in many ways, this is an assessment of how much hidden knowledge is still around. I really would like to see no hidden knowledge. And finally, we have the accessibility test. So this is, would a beginner grad student be able to use and extend my code with guidance? So here I'm thinking about how hard is my code? Do I provide entry points for people that are maybe not super experienced to be able to do something with that? So this is not about the long-term survivability of the project. This is about thinking, okay, what are the entry barriers? Where would anyone go if they wanted to use my code? What would they do? Is there something in place for them? Or someone has to tell them how it works? So I think if you think about these questions, you look at your documentation, you look at your examples, you look at your tutorials, you'll get a sense of whether your code will survive and will be accessible. If not, well, you can take action. So finally, action is my keyword. If you want to take anything away from this talk today, I urge you to start thinking of scientific software not just as a tool, but as a scientific contribution itself. Scientific software in the 21st century is critical. We shouldn't just think about papers. Software is very important. I'm very biased, so maybe we can discuss that, but software is very important, and by itself is a massive contribution to science. And second, keep in mind the people that are using your documentation, how they're accessing that documentation. It's not just one person. It's not just one way to access documentation. And if you do that, I'm sure your code will end up being better. And with all of that, you can get in touch with me. That's my email. There's apparently my LinkedIn address or handle, whatever. That's my picture, or you can look at me. And I'm happy to take any question. But since this is the end of the talk, you feel free to live and enjoy your evening if you want. Thank you.
Having been a grad student at Caltech back in the lower Paleolithic, I have so many thoughts. So, questions? There we go. You're the bravest person in the room.
Yeah, thank you so much for your talk. So I guess when you were giving this presentation, it had me thinking a lot about the whole AI model card debate. And there's a lot of conversation about best practices for model cards, things like that. Are you approaching that in the same way, with JOS and that sort of thing? Are you putting out documentation, developing templates? What are you doing so it makes it easier for people to provide the right kind of documentation?
Yeah. So one of the things I'm doing is I'm speaking in this room to people, and I try to, I'm an individual. I'm not paid to write documentation. I'm paid to develop software. So there's a growing group of people that recognize that this is an important thing to do. We call them research software engineers. Maybe they're not the right title. But I think over the past maybe 5 years, there's been more organized push, at least in US and Europe, to think about good practices for research software engineering, so for scientific software. So as a community, we have started developing something to help other people. But this is difficult, and there's a fundamental problem that incentives are not aligned. Especially if you're a student, well, you can either write documentation or you can write papers, and you're going to write papers because that's what gives you jobs. So, this is, I think, advocacy is one of the important things that we can do, is really making sure that people recognize that there is a lot of value in good software, not just in software. This is not a good answer. I think we should eventually start developing, templates, good practices. But at this stage, I think we're, still in trying to make sure that people recognize the value of what we're doing. Yeah. I think there's a.
So I think what you're telling us is that in the future we should think of our scale talk as a standalone scientific contribution. Thank you so much.
Yes.
I've been involved with software documentation for a very long time, and I think it needs to start before the software. The documentation should come first, because you need to know what it is you're trying to write before you write the software. If you write the software first and document it afterwards, you'll never do it. You'll never go back and do it right.
Yeah.
So you've got to start ahead of time and think about it all. One thing that's always fascinated me about documentation, I can buy a microchip that's a couple of centimeters or a couple of millimeters on a side, and I'll get 500 pages of documentation. I'll buy a piece of software with 200,000 lines of code, and it'll get a getting started page.
Yeah.
So there needs to be something there.
Yeah, so I think that goes back. Thanks, your comment is great. I love it. Because I think this is one of the special things about scientific software. I wish I could write documentation before starting my code. I cannot do it. I don't know where my code is going. This is a research project. Most scientific software is not waterfall. It's something that is very organically growing with time. So it's really, really, really hard to write documentation beforehand. And most code is shared, is handed down from one to the other person. So you cannot just write documentation. It's harder. So I wish I could just write documentation beforehand. Yeah.
But we could go back and get it right.
Yeah. Yeah, so the conversation for the recording, if there's a recording, is about, well, you don't know where you're going most of the time, so probably you cannot write documentation beforehand. And I resonate with that, at least in scientific software, where in many cases it's a research project.
Anybody else? Even if we can't write it in advance, we could still go back and get it right. And at least 30 years ago, that we did not do that.
Well, thanks everyone for being here. I'm happy to chat more about anything if anyone wants to. Thanks.